Up to
Okay.
you.
Okay, well, I'll get us started then. Welcome everybody. Thanks for joining us today in our OSIGp technical webinar. My name is Cathal Garibi, and I'm a committee member of the OSIGp committee of SUT based in Perth. So today's talk by Dave Walsh is going to be on the combined CPT and NMR tool for the enhanced geotechnical characterization of the seabed. So just a bit of housekeeping just to keep the flow good in the presentation. If I could ask everyone just to keep muted throughout the session and maybe just leave your cameras off as well, just so there's less distractions going on. We do have a Q&A box that you can access through the Teams portal. So if you have any questions, you can certainly ask them within there. But Dave is also happy to take questions throughout the presentation. So if there's something that you want to raise during the session, maybe just use the raise hand button on Teams, and we'll try and get to that question as we go. So just a little bit about SUT. So the SUT, the Society for Underwater Technology, is a not-for-profit, multidisciplinary learning society that brings together organizations and individuals with a common interest in underwater technology, ocean science, and ocean offshore engineering. It was founded in 1966 in the UK, and it has members from more than 40 countries. The SUT includes engineers, scientists, students, underwater operators, and technologists working in these areas. The Perth branch of SUT was formed in 2004. It has approximately 200 individual members and 40 corporate members within Australia. And 15 global members have operations within Australia as well. So the OSIGp is a subcommittee of SUT, and we promote the technical advancement and knowledge sharing amongst academics and practitioners in the fields of the 4Gs, the 4Gs being geology, geophysics, geomatics, and geotechnical engineering. The OSIGp committee in Perth, we liaise closely with our colleague branches in both UK and Houston to create a global network of professionals working in the subsea 4Gs. This is our current OSIGp committee for the 2025-26 years. So I'm a committee member, Nicole, who's also on the line, is our vice chair and secretary, and the rest of our committee there. So if you're interested in hearing what's going on in the OSIGp committee within Perth, feel free to join us on LinkedIn. Either have a search us up on LinkedIn, or you can use that QR code to join also. Just a few details of upcoming events. Obviously, these are purely Perth-based. Unfortunately, we can't host these online. But if you are in Perth and you're keen, please feel free to register. On the 25th of June, we have our OSIGp quiz night. So come along, impress your colleagues, clients, competitors with your knowledge of OSIGp geoscience themed plus general knowledge quiz. It should be a good fun evening. It'll be hosted at the Shoe Bar in Yegan Square. People who are in Perth will be familiar with that. You can register as an individual or register your company's table if you want. And again, you can use that QR link or go via the SUT website to register. In July, the 24th to 25th of July, we have our biannual OSIGp Geohazards and Geotechnics course. So this is the 2-day course that we run every second year and explains the offshore geology, geohazards, and geotechnical engineering, adopting a holistic approach to show how they interact and how an improved understanding of these three disciplines can lead to an optimized infrastructure solutions with applications in the offshore oil and gas and offshore wind developments. Registrations for this will be opening soon. So if you or you know anyone who might be interested in this, feel free to keep an eye on the SUT Perth website. Registrations will open. Now that that's out of the way, just get into the presentation session itself. So today's presentation is going to be, as I said, going to be on the combined use of CPT and NMR tool technology. It's going to be presented by Dave Walsh. He's the founder and president of VistaClara Inc. in the US. So Dave is the founder and president of VistaClara, where they've spent the past 22 years focusing on the development and commercialization of NMR geophysical instruments. Dave's contributions to the field include the development of multi-channel surface NMR instruments and processing methods for groundwater investigations, the development of small diameter, low-cost borehole NMR logging tools for hydrological investigations, development of direct push and CPT-based NMR technologies for geotechnical and hydrologic characterization of sediments, and the development of nuclear quadruple resonance sensors for the detection of buried explosive. Dave earned their PhD and MS degrees in electrical engineering from the University of Arizona and a Bachelor of Science degree in electrical engineering from Iowa State University. And without further ado, I'll pass over to Dave to start the presentation.
Thank you very much. And thanks to everybody for spending the time here today. All right, so this talk is on a combination CPT and NMR tool for enhanced geotechnical characterization of the seabed. And as we said, I'm happy to take questions anytime through the discussion here. Let's see, can everybody see this okay, the outline?
Yeah, all good, Dave.
Yeah. Okay. All right, so we're going to start with the motivation for this tool development, and then I'm going to include a short background on nuclear magnetic resonance, the technique. It's also abbreviated as NMR. Some people drop the N because it's sometimes confused with a nuclear radioactive technique, which it is not. And then I'll get to an overview of the tool itself, and I'll have some examples from using this tool on land, inshore, and in an offshore setting. And finally have some discussions of benefits and applications for various offshore investigations. And it's about 25 slides, so it's not too long. Hopefully we'll get through it pretty quick. So I'm going to start with the motivation for this development. And the first few slides I'm going to present here are actually not mine. These were put together by Roy Santos, who was until recently at Ørsted. And they did their own independent analysis and economic and technical analysis of what their needs are and what type of technology would help them and the industry in general going forward. So there's an increasing need for geotechnical investigations, particularly because of the rapid growth of offshore wind energy. So this is the current, a relatively current estimate of the growth trend over the next 15 years. So from the developer's point of view, one of the biggest challenges they have is that the geotechnical investigation stage is a big bottleneck for their development efforts. So there's just not currently, or at least in recent future, and in the foreseeable future, there's going to be a limited supply of the assets that are required for traditional geotechnical investigations. And there's also pressure to get offshore wind energy projects up and running and developing power quickly. Pressures in part due to finances, interest rates, etc. Okay, so the traditional site investigation technology and workflows are considered to be too slow and too inflexible to support the pace required for new offshore wind development. So Ørsted and probably others have identified Seabed CPT systems as a key enabling technology that can help speed up that geotechnical investigation stage and hopefully also improve the accuracy and reliability of the data that's acquired. So some of the parameters, the key parameters that are known to drive the cost of foundation engineering include these: soil strength, soil stiffness, density, and stratigraphy. And Orsted looked at, okay, what sort of technology development would impact, in particular, the ability to measure those or determine those properties. So they identified two technologies in particular. One is improved seismic ZPT, and the other one was in situ NMR. And so we're going to talk about in situ NMR today. So as part of their internal research, Orsted and another institution also performed some laboratory work to establish the relationship and the suitability of using in situ magnetic resonance measurements to estimate, in particular, density. So, and they found through these measurements that in situ measurements of NMR measurements of porosity combined with the a priori assumption of dry density is a very accurate way and a very precise way of estimating the bulk density in situ. So what you see here on the right is just a bunch of different samples that have been used to estimate the bulk density from the NMR measurement and compared to other methods like, gravimetric measurements in the lab. And so the green, sort of that green, tight green spread there, that's sort of the standard deviation line or the variance of using the NMR, in situ NMR, to estimate density, versus this sort of purple line, that's versus the traditional method of using just CPT alone and then follow on laboratory work. So that's a big difference in the in the uncertainty of that particular method. So so what is the value of reducing that uncertainty? Well, they even went one step further than just like establishing the differences in uncertainty. They looked at how much money they could save if they started to collect in situ NMR data and use that for, at a minimum, just using that to prepare to reconstitute their soil samples for their laboratory tests of actual stress tests. And so for foundation designs in particular, the bottom line is they come up with an estimate of a conservative estimate that they can save up $9 million for every 100 turbines, just in terms of the savings of steel, the cost of steel. So if they don't have to over-engineer their foundations to cover the uncertainty from traditional methods, they can save a significant amount of money just in the cost of steel. Similar results with assessments of what's the economic advantage of applying CPT and NMR for cable route surveys. So that's sort of the overall overarching motivation for this. I guess in this case, we've got an assumption that if they acquired a CPT and NMR every kilometer, they could save half of their vibrocore costs, soil sampling costs, and save $500,000 for a 100-kilometer cable route. Okay, so I'm going to talk about nuclear magnetic resonance. So this is probably new to a lot of people on this call. So if anybody has any questions when I'm going through how NMR works, please just pop up question, and one of the moderators will relay that to me. So NMR is basically a method for detecting hydrogen. So it's inherently non-invasive, and what we're doing is we're detecting the hydrogen atom attached to the H2O molecule. And we detect basically its magnetic moment. So not all atoms have a magnetic moment. Hydrogen does, because it has a single charged particle and it's spinning. So it's kind of like having a little current loop, and that creates a dipole moment. And that's what we're detecting, the magnetic moment of the hydrogen. So if you've got a hydrocarbon fluid, you would also detect that hydrogen through NMR. So this method has been used in pharmaceutical industry and organic chemistry very widely for about 50 years. It's a key sort of analytic method for probing the structure of organic molecules. NMR is also the basis for medical MRI. So if anybody here has ever had a medical MRI scan, you were basically subjected to an NMR measurement. And in this case, you have a certain type of instrument that has a superconducting magnetic field generating coil. The patient goes in to the middle of that coil, and NMR measurements are used to basically map out water and tissues in the human body for the purpose of diagnosing injuries and disease. So in our case, we're using the same physics, but in a different form. So we're using, and for a different purpose. So we're basically using NMR to detect water that's in the ground, and also to determine sort of what are the properties of the sediment that holds that water and that can transmit that water. So the relationship between NMR and hydrogeologic properties is really what sets it apart from other geophysical methods and other geotechnical methods. So here's how this works. So basically NMR is detecting water in the pore space. So basically you don't detect the rock sample or the sediment sample itself, just the water that's in between the pore spaces, and in some cases adsorbed to the material itself. So if you've got twice as much water in your sensitive zone of your instrument, you'll get twice as big of a signal. So your NMR signal has a form like this. It has a particular resonant frequency, it has an initial amplitude, and the signal decays over time. So that initial amplitude is directly proportional to the amount of water that's in your zone. So it's a direct and linear measurement of porosity. And in geotechnical terms, it's a direct and linear measurement of void ratio, water-filled void ratio. So that's really interesting and valuable on its own. But the other thing about the NMR signal is this decay time. So the thing that governs the decay time is actually the pore size. So water that's in large pores like this one here, the NMR signal exhibits a long relaxation time, a long decay time. Conversely, water that's in very small pores like these, the NMR signal exhibits a very fast decay time. So just by looking at the nature of that relaxation curve, you can tell if the water's bound in very small pores or if it's available to move or to drain in very large pores. So ultimately, it comes down to what happened to this graphic? Oh well, what happened here? But ultimately, NMR is giving you key hydrogeologic properties of sediments and rock formations, including water content, porosity, a relative pore size distribution, and also estimates of the effective porosity or the drainable porosity, and even hydraulic conductivity. Okay, so that's the background on NMR. We can come back to that if there's any questions. So here's the concept between the CPT and NMR tool combined. So the concept is you have a Seabed deployed CPT system, and you have a single tool that gets pushed down from that CPT rig. It measures CPT on the way down through a traditional cone, and it measures NMR response while retracting back up. So you get both sets of data in a single push from the same sensor. And it's done from a Seabed deployed CPT rig. So a couple of the engineering challenges to develop something like this is the NMR sensor itself has to be made very small and still maintain a reasonably large diameter of investigation. So this particular type of NMR sensor actually senses in a very thin cylindrical region that is displaced from the side of the tool. So this is important because you've got a lot of compaction and disturbance happening right in the immediate vicinity of the CPT tool. So the NMR sensor is actually not sensitive there. It's sensitive several inches outside of that. Okay, so the second engineering challenge here is that you have to have a non-conductive section in your housing. So NMR works by basically transmitting and detecting alternating magnetic fields at relatively high frequencies. And those magnetic fields will not penetrate a metal housing. So there has to be a section of this housing that has a non-metallic section. And the whole tool, of course, has to be able to survive these very large static pushing forces. In our case, we're pushing with up to 100 kilonewtons with this tool. So on the right here, this is actually an early prototype of the CPT NMR tool. You can see the cone down here. It's got a 15 centimeter cone. And in the body section of this tool, in that yellow section is where the NMR sensor is. Okay, so the current specifications, in case anybody's really interested, it's about 5 feet long. That's from the tip of the cone to the top of the drive head. It is nominally 48 millimeters in diameter at the maximum point, which is like right here. You can push it with 36 millimeter OD or 45. You could push it with 55 too. Whatever, you just got to change your drive head for whatever type of push rod you're using. Got 15 centimeter cone. The NMR sensor has very high vertical resolution, about 5 centimeters. Short echo spacing, that's an important parameter for being able to measure water in silts and clays. And that's about it. Okay, before I get to any data examples, I just want to kind of explain what you're going to be looking at with the NMR data. So the raw data, as a function of depth, this axis is depth. The raw data is actually in time, units of time. So you've got basically an amplitude. You've got a signal that's decaying from left to right. So wherever you see a long signal like you do here, that's because you've got water in large pores that has a very slow decay time. And conversely, here you've got water that's decaying very quickly. Okay, so the first step is to fit this data to a multi-exponential model. And that gives us this plot, which we call the T2 relaxation time distribution. And you can look at this as basically a relative pore size distribution. Wherever you see like a brighter yellow or red, that means you've got water at that relaxation time, which, remember, long relaxation times over to the right, that corresponds to water in large pores like sands and gravels. Water way over to the left, that corresponds to water in small pores like silts and clays. So essentially, if you start at the left here at about 1 millisecond, you're looking at hard clays, soft clays, silts, fine sands, medium sands, coarse sands, and if you had any gravels, you'd have a signal way over here. Okay? And then finally, if you integrate this energy in these 3 different zones, like less than 3 milliseconds, 3 to 30 milliseconds and above, then you can separately estimate water that's bound by clay-bound water, water that's bound by capillary forces, and water that's mobile or drainable. So in this plot, you've basically got a stacked total water content estimate is that black line. And you've got separate estimates of the different bound and mobile fractions of that water. Okay, here's an example of using the CPT NMR tool on land. This was in Kansas. We have basically unconsolidated sediments down to about 14 meters. There's or 15 meters. There's shale at the bottom of that. So in this case, we have a water table at about 5.5 meters. And these are mostly fine sediments in the upper zone here. So you see that even in the unsaturated zone, we're detecting a significant amount of water content, and that's expected because you've got fines there and they tend to hold water even when it's unsaturated. Your CPT data is over here. It shows a lot higher friction because this clay is drier. It's got higher friction to it. Then below the water table, we have mostly fine sediments to about 8.5 meters, although there is a little bit of sand right here. And then there's a pretty contiguous sand and gravel aquifer. Do we have a question? If not, I'll go forward. So there's a sand and gravel aquifer here. You can see this clearly from the relaxation time. So comparing the CPT and the NMR data, they're all consistent with each other. CPT data is basically showing you, okay, how much force do I need to push through this stuff? How much friction am I experiencing? And do I see something that indicates some sort of a hydrostatic line? Whereas the NMR data is giving you quantitative numbers on volumetric water content, porosity, effective porosity, and hydraulic conductivity, and an ability to really see this finely structured differences in the distribution of sediments here. A second example is using this tool from a jack-up barge over a lake in New Orleans, near New Orleans, Louisiana. In this case, we got very soft lake bed sediments. Not terribly interesting, these curves. It's very soft, not much resistance, not much friction, except for where you have some sands mixed in here and there. And but with the NMR data, you also get total porosity and total water content. And you can see some interesting differences, like see where you've got a little bit more sand mixed with silt, you have a lower porosity. And that's because you have the sediment is less well sorted, right? And that leads to a lower porosity. And you can also get quantified estimates of hydraulic conductivity. So I have two more examples, and they're from an offshore wind cable route survey, which was performed last December off the coast of the United States. So on the right, you have your CPT data, which I'm sure everybody here is familiar with CPT data. So I like to kind of tell people or ask people when they show this slide, all right, what can you determine from the CPT data alone? So I can determine, well, it looks like there's something coarse down here because there's a hydrostatic line here. Okay, that indicates we're in permeable materials. Tip resistance goes up at that point, friction goes up. But why is the friction continuing to go up here and the tip resistance going down there? And then what's happening below there? Pore pressure is kind of weird. Tip resistance is continuing to go up. Friction is high, but not directly correlated with that. Okay, so there's some ambiguity in the CPT data alone. So if you add the NMR data, what does that tell you? Well, definitely you've got soft sediments here, although those relaxation times are not that long. These are silt-like relaxation times, not clay-like. And then there is a pretty well-sorted sand deposit here. It actually trends from a little bit finer sand to a little bit coarser as you go through it. It also gets particularly well sorted right here. And then below that, you have an interesting mix of pore sizes and indicating different sediment grain sizes mixed together, or perhaps very thinly interbedded. And so you also have estimates of hydraulic conductivity, which range up to 100 meters per day, a couple hundred meters per day down here. That's pretty high. All right, and the total porosity, keep an eye on the total porosity here because this is an indicator of the density. Okay, one more example. Okay, in this case, we've got soft sediments again, and then boom, we hit this increase in the resistance. The friction also rises somewhat, but it's a little bit offset, delayed in depth versus the increase in friction in tip resistance, sorry. Got the indication of a permeable zone here from the hydrostatic line, again down here. And then it's again a little bit ambiguous what's happening below that. So one question I usually ask people, which of these two sand units has a higher density? So I'll let you just guess. And then I'll show the NMR data. So this sand unit has a lower porosity. See that 30%? Whereas this one's more like 40%. So this is actually has a higher density. And it's also coarser. These are much coarser sands. You can see that from the relaxation times. That's a pretty long relaxation time compared to this down here. And then up in these soft sediments, you've got more like 60% porosity through there. Previous site, 50%. And then in between these two sand units, you've got some very high porosity data point right there at about 70%. So it's some very soft, very watery material right there. And even down here, you see that it's mostly sand in this lower section where things get a little confusing with the CPT. Mostly sand, but there are some fines mixed in. And so it's shown clearly in the NMR data. In fact, you can tell what the fraction of the fine pore sizes are compared to the coarse-grained pore sizes. Okay. So we see the benefits of this particular tool compared to existing and traditional methods of sampling the seabed. One, it's an in situ measurement. You don't have any disturbance or alteration of the sediment properties. It's measuring it in its native state. Two, it's continuous. You don't have loss of sample like you're always going to have with soil sampling, in particular with sands. Three, it's rapid. You can collect the CPT and the NMR data in a single push. It really doesn't take a lot more time than collecting the CPT data on its own. And when you're offshore, the big cost is, of course, the cost of the vessel and the crew and all those other things. It's not really the CPT equipment that's costing all the money. It's all those other costs that go into getting that thing out there. The results are immediate. So, I mean, all the data I've shown you, when that data is being collected, you can see that final result in real time as it's being collected. So there's really no delay in having completely end product that you can analyze and start doing some engineering analysis of. So lower cost, it's faster because it's a CPT measurement. It's faster than drilling and sampling. It's faster than borehole logging. And there's no cost for transporting samples or for doing laboratory analysis. And finally, I think the NMR will over time be seen to be able to provide an improved ability to classify sediments compared to just having the CPT alone. So finally, just a few potential like sort of real world applications of the NMR in these offshore wind applications and other energy applications. So one is density. In situ density is an important parameter to try to, for foundation design in particular. And with sands, if you're relying on core sampling, the core samples, the sand samples are frequently lost. They're disturbed. They're compacted in some cases. They get looser during transport, whatever. So it's really there's a lot of uncertainty when you take a core sample, a fiber core sample, and send it to a laboratory, and then use that sand sample for stress testing. So if you've got an in situ measurement of the porosity, then you can combine that. You can basically use that information to recreate that same condition in the lab on that core sample that you do have, and then perform your stress testing. So this is a way that you can potentially reduce project risk and also reduce project costs because you don't have to over-engineer the foundation. Okay, second thing to consider is some types of foundations, hydraulic conductivity and drainable porosity are other important variables to how the foundation is going to settle or over time, or how it's going to initially be installed. So for example, suction bucket, where you have to pump water out and that water is coming through the sands and whatever the sediments are. So NMR provides quantitative estimates of hydraulic conductivity and drainable porosity. And those are useful if you want to model this, what's going to happen. So for export cables, I don't work for an energy company, but I know people who do, and they say basically these days they just can't wait for the laboratory analysis. I mean, they rely on CPT and soil sampling and laboratory analysis, but they gotta order these cables years in advance of when they need them. And current practice is just too long of a delay to be able to use any of that information from the laboratory. So if they can get data quickly at the very, very early part of the site investigation using CPT and NMR and get a lot of these risks identified, particularly like organic rich sediments and peat, which can cause overheating of cables, then that's a potentially big deal for reducing risk of cable failure in the future and reducing costs of cables in the current. Okay, finally, there's other applications other than this has been kind of focused on offshore wind, but it's just a general problem. Seabed investigations for pipelines, cables, hydrogen, drilling platforms. They all have similar site investigation needs. So all of these benefits of combining CPT and NMR into a single tool, they're going to be able to transfer to these other energy applications as well. All right, so in conclusion, this development was driven from the industry itself. We actually didn't. We're a small business in the U.S. and we didn't actually come up with this idea ourselves. People from the energy industry, offshore wind industry in particular, came to us and asked us if we could do this. And it's driven by that sort of the bottleneck right now. That's the bottleneck caused by the lengthy geotechnical investigation phase. So combining CPT and NMR in a single tool can resolve some of the key challenges that industry is facing. And combining those measurements can reduce the scope and delays of onshore lab programs, reduce uncertainty, and reduce the engineering costs associated with that uncertainty. Thank you very much, everybody, for your time today. I'm happy to answer any questions, go over anything else we have. We did get some support from the United States Department of Energy, and we appreciate that.
Thanks, Dave. That was a really good talk and really, really interesting technology with a lot of benefits there. I don't see any questions pop up yet, so maybe I'll get the ball rolling on questions, and if anyone wants to jump in, can raise their hand and we can go through questions that way. You mentioned that the recording for the NMR happens on the extraction of the tool. The extraction rate, is that similar to our kind of insertion rate of 20 millimeters per second?
It could be. You could go that fast. The data that I showed you was collected at a significantly slower rate because we really wanted to get these first early, especially the cable route survey, we wanted to get some really nice looking data. And so we took about 45 minutes to coming out over that 6-meter interval. But like the one over the lake bed, that was significantly faster. It's always a trade-off with a tool, an NMR logging tool. You can trade off logging speed or measurement speed for vertical resolution or for signal to noise ratio. So the slower you go, the better resolution and the better the data quality. But everything costs money. Time is money. So it's definitely easier to go fast. You're just going to give up some of your signal to noise ratio and or some of your vertical resolution.
And obviously with signal to noise ratio, if that's going up, it makes interpretation of that data a bit more complicated or a bit more uncertainty in there.
You have random noise that's always part of your measurement. And so the longer you take, the slower you go, basically the more signal averaging you're doing. And that basically reduces the noise, the random noise in your data. And yeah, the downstream derived estimates of water content, porosity, hydraulic conductivity. They're all going to get more precise as your noise drops.
And in terms of the tool housing, you mentioned it was non-conductive material. Is that kind of like a plastic type of material, or?
It's layered. It is a composite. It took some time to develop something that works really well. I can say that some early prototypes of some material didn't hold up too well and broke, and all sorts of things. So we came through this through a normal research and development iterative process, and it's held up well. It's going to have a finite life because every time it goes past a boulder and scrapes, it's not steel. It's going to get gouged, and over time, it's going to be a replaceable item, that housing.
And did anyone else in the audience have any other questions for Dave on the talk? I guess in terms of the NMR technology itself, that's been well proven in terms of the kind of density estimates, permeability estimates, and things like that. Is that fair to say that the technology is well proven?
Yeah, it's been used in oil and gas business for 30 plus years. It's a mainstay measurement there, and they're using it mainly for reservoir characterization. What's the permeability? What's the porosity? What is the fluid type? What's the oil fraction? What's the water and gas fraction? So that's the main use, and they're the pioneers of using NMR for subsurface. And we've been not working in the oil and gas business. We've been focused on introducing NMR to environmental and groundwater investigations mainly for the past 20 years. And in sediments in particular, unconsolidated sediments, the relationships between your NMR measurements and hydraulic conductivity are very stable and very repeatable. When you start getting into consolidated rock, then you have to have like individual models for different types of rock. But we're talking about sediments here. And then, the porosity and the volumetric water content, that's actually a direct measurement. So it's no formulas involved. You're just directly measuring it with NMR. There's a question.
Yeah. Feel free, Kanaki, if you want to ask your question.
Yep. I know you mentioned that we are trying to combine these two tests as part of a industry or a construction phase demand, that they can't wait for those individual tests to be done, and mostly driven by procurement of long lead items. Are we losing any quality, or are we losing on a qualitative aspect if we are combining this?
Well, I would say combining CPT and NMR into a single tool doesn't cost you anything really, because you're going to get CPT anyway, right? They're going to do the CPTs on all these foundations. They're going to do them on the cable routes. They're going to do all as much as they can. They're going to do the CPT. So it's more a question of, can you substitute the NMR? So what I'm saying is, if you're doing the CPT and you're getting the NMR at the same time, that's a real bargain. The question is, can you forego some of the other stuff, like some of the vibrocore sampling and some of the laboratory work, if you've got more confidence from your NMR and CPT data? And it's a little bit outside of my personal and professional experience, but the slides we showed at the beginning were actually not our slides. Those I got from Roy Santos, and he did that work when he was at Orsted. So they are pretty confident in that analysis, and that's why they're starting to spec it on their projects.
Okay, yeah, that was That was the only question I had. Thank you.
Thanks.
Anyone else in the audience have anything they want to ask? Oh, we have Dave here.
Let's see, is there anything in the Q&A button?
Oh, yes, there's something.
There is
Okay.
a question in the chat from Julia saying, really impressive presentation and technology. Congratulations on developing such an innovative tool. I look forward to seeing more of it in the future. How was the industry been responding so far? I guess outside Orsted, as you mentioned, who is starting to spec these applications.
Yeah, Orsted's kind of, they're not doing a lot of geotechnical investigations this year for various reasons. They've been a strong supporter of this from the start. I've been sort of doing a version of this presentation for about 4 months now, starting in January. I think we've briefed about 20 different organizations, and many of them are see value in it and are very interested in it. There's about half of the audience is typically skeptical that they don't need it, right? But I guess it's new, and so we are, we are moving forward with technical developments and integration with different types of CPT machines at the moment, and trying to make it available and start to have it seeing it get used a little bit more widely, hopefully this year. There's another in the chat Q&A, 2 questions related to the T2 distributions. This is from Yannick. Can the T2 distribution be directly calibrated to particle size distribution, for instance, to determine the fine content? The answer to that is you can, but you're not directly measuring particle sizes. What you're measuring are time decays that are correlated with pore sizes. So if you've got a well-sorted material, like you've just got a bunch of fine sand and there's no fines mixed in it, then you can make that relationship, right? Because the pore sizes are going to be governed by the grain sizes or the particle sizes. But if you've got a poorly sorted mixture of particle sizes, then your pore size distribution is not the same as your particle size distribution, if you know what I'm saying. Like if you've got a bunch of gravel and cobbles, those are large. And then in between them, you've got a lot of fine sand and silt filling those spaces. You're not going to see any pore sizes that are the same size as those boulders or those cobbles or whatever. So generally, you can try to make that relationship when you've got well-sorted materials. Mineral content affect the prediction of NMR results. Excellent question. So NMR can be affected by sediments that have high magnetic susceptibility. And I think the threshold for that's like somewhere in the range of 10 to the minus 3, especially 10 to the minus 2 SI units. So that's just kind of a number where we start to see significant effects on the NMR signal. So magnetite, volcanic, sediments derived from volcanic activity, stuff like that, they can have high magnetic susceptibility. And if it gets very high, it will definitely cause you to underestimate the water content. Any other questions or comments on that?
Yeah, we'll just throw it, let the floor, give them a chance to ask any more questions before we wrap up. No? It seems everyone's questions have been answered. Curiosities have been quelled already. Oh, getting something in the chat here. very impressive development and technology. I look forward to seeing this technology integrated into current CPTU works, especially in the Australasia region. Thank you. Someone's asking, can we get access to the recording? Is this, I'm not even sure if this has been recorded, is it, Nicole? Or,
I was just looking, and it seems it had, even though the recording has stopped at 10:42. No, maybe not. Oh yes, I will have a look. I'm actually not sure.
If anybody wants, they can email me. I can send this presentation by email.
Thank you.
Yeah, Nicole, it's still recording, so you're good.
Okay. Yes, I got the awesome. So yeah, we can make the recording available for the attendant if Dave is okay with that, obviously.
Yes.
Awesome, Dave. Thank you.
Okay, well, if there's no more questions then, maybe we'll wrap it up there. Just obviously we'd like to thank everyone for coming along to the presentation today. And especially thanks to Dave for taking time out of his evening there in the US to give this talk, which is really informative, and I think people got a lot out of it. So
Great.
thanks again, everyone. Please keep an eye